Right now, as you rest, your body carries warmth, movement, and life. But there are places in the universe so cold that motion itself nearly disappears. Places where the very activity of atoms slows to an almost unimaginable stillness. Tonight, in the quietness of this moment, let us journey together to the coldest places that exist. Not the cold of a winter night, or even the deep chill of Antarctica, but a cold that reaches toward the absolute limit of what is physically possible. A cold so profound that atoms almost come to rest in their endless motion. A cold that lives in the vast spaces between stars, in the fading remnants of ancient nebulae, and in the laboratories where scientists carefully approach the final fractions of a degree above nothingness. Before we travel to these distant and delicate realms, we can take a moment to understand what cold truly is. In everyday life, we often think of cold as something that exists on its own, perhaps as the simple opposite of heat. We feel it on our skin, see it in frost on glass, and recognize it in the sharp air of winter. Yet physics offers a gentler and more subtle picture. Cold is not something that exists by itself. It is an absence of energy, of motion, of the tiny vibrations that give matter its life and structure. Everything in the universe is always in motion. The chair beneath you, solid as it feels, is made of atoms quietly vibrating in place. The air around you is filled with molecules moving swiftly and constantly, colliding countless times each second. Even the ground beneath your feet contains atoms softly oscillating, their motion creating the sensation of solidity. This movement is thermal energy, and temperature is simply a measure of how much of this motion is present. Heat is the presence of kinetic energy at the smallest scales. Cold is the gentle fading of that motion. The theoretical limit of this fading is known as absolute zero, resting at -273.15 degrees Celsius, or zero on the Kelvin scale used by scientists. At absolute zero, all thermal motion would seem to fade away, and atoms would settle into their lowest possible energy state, at least according to classical physics. But the universe is more subtle than classical ideas suggest. Even at absolute zero, quantum mechanics tells us that a faint motion must remain. The Heisenberg uncertainty principle requires it. This gentle, unavoidable motion is known as zero-point energy, the smallest flicker of activity that allows matter to remain matter at all. Because of this quiet quantum trembling, absolute zero is not simply difficult to reach, it is fundamentally impossible. It is a boundary woven into the fabric of reality itself. And still, the universe comes remarkably close. In the deep expanses of space, in rare and delicate regions, temperatures drift toward this ultimate limit. The background temperature of the universe itself, the lingering warmth from the Big Bang, has cooled over billions of years to just 2.7 Kelvin. That is only 2.7 degrees above absolute zero, colder than anything that forms naturally on Earth. This faint radiation fills all of space, a soft whisper of microwave light left over from the universe's brilliant beginning, now cooled to barely above nothing at all. Yet there are places even colder, places where matter and energy align in unusual ways, creating conditions that come astonishingly close to the lowest temperature nature allows. These are the realms we will gently explore together, drifting slowly through the cosmos and noticing the quiet beauty of the universe at its coldest. Here we begin to see that cold is not only the absence of warmth, but a condition that reveals new physics, new forms of matter, and new ways for reality to arrange itself. And as we move deeper into these frozen frontiers, a small and curious paradox appears. The coldest place ever measured by humans does not exist naturally in space at all. It exists in a laboratory in Massachusetts, where scientists have cooled atoms to less than a billionth of a degree above absolute zero. This invites a few gentle questions to rest with. What does it mean that we can create conditions colder than the cosmos itself? What might this say about the relationship between knowledge and nature, between what already exists and what can be brought into existence? The journey toward understanding cold is also a journey through the history of science. For a long time, heat was believed to be a substance, an invisible fluid called caloric that flowed from warmer objects to cooler ones. Cold, in that picture, was simply the absence of this fluid. It was not until the 19th century that a quieter and more accurate understanding emerged. Heat was motion, energy in one of its most fundamental and widespread forms. With that realization, new doors opened. If heat was motion, then cold was stillness, and absolute zero seemed like the point where all motion would finally come to rest. Or would have, if quantum mechanics had not introduced its own subtle and beautiful complications. When we reflect on extreme cold, we are really reflecting on the foundations of reality itself. We are observing what the universe becomes when nearly all energy is drawn away, when matter approaches its lowest energy state, and when the restless dance of thermal motion gives way to the delicate patterns of quantum behavior. In the coldest places, physics begins to feel unfamiliar. Liquids can flow without friction. Metals can conduct electricity without resistance. Light can slow dramatically, and under special conditions, even appear to pause. Atoms can gather into shared quantum states, behaving less like separate particles and more like gentle, overlapping waves. The rules that guide our warm and energetic world begin to soften. These transformations occur not because something new is added, but because something is gradually removed. Energy fades, motion quiets, and within that stillness, the quantum nature of reality becomes easier to notice, as if the universe, when cooled, slowly reveals a deeper layer of its true character. Beneath the constant motion of everyday temperatures, a quieter nature waits to be seen, hidden behind the restless energy of thermal movement. So now we begin our journey to the coldest places. We will move slowly, allowing each location to reveal its character and its quiet mysteries. We will start with the coldest place known in the natural universe, where a dying star's final breaths create temperatures that drift toward absolute zero. From there, we will wander through the chill of deep space, across the frozen surfaces of distant worlds, and into possible futures where the universe itself cools toward a distant and gentle end. Along the way, we may discover that cold is not simply an ending, but also a beginning, a gateway to states of matter and forms of existence that cannot emerge in warmer conditions. Settle into comfort. Let your breathing become slow and easy. The universe is vast, cold, and quietly strange, and there is no rush as we explore it together. In reflecting on these frozen realms, there can be a certain peace, the peace of stillness, of silence, of drawing closer to the most fundamental resting state of existence itself. Let us step softly into the cold and notice what wonders are waiting there. Far from Earth, about 5,000 light-years away in the direction of the constellation Centaurus, there is a region colder than any other place we have found in the natural universe. It is known as the Boomerang Nebula. Through small telescopes, it appears faint and ghost-like, uneven and hard to define. But in images captured by the Hubble Space Telescope, its true form becomes clearer, vast outflowing shapes of gas and dust spreading into space, lit by the fading star at their center, forming gentle curves that once reminded observers of a boomerang, or perhaps the soft outline of a bow tie drifting in the dark. More recent observations have revealed an even more intricate structure, with layers and streams of matter flowing outward in patterns that hint at turbulence and intensity in their origin. At the heart of this nebula, the temperature falls to about 1 Kelvin, just 1 degree above absolute zero. This makes it colder than the cosmic microwave background radiation that fills all of space, colder than the darkest voids between clusters of galaxies, and colder than any other natural place we have yet discovered in the observable universe. How such an extraordinary region can exist is a story shaped by stellar death, extreme physics, and the unusual behavior of matter when it expands rapidly into near emptiness. The Boomerang Nebula is known as a pre-planetary nebula, a brief and delicate phase in the life cycle of certain stars. At its center is a star somewhat like our Sun, though a bit more massive. This star has used up the hydrogen fuel in its core and has begun the long process of transformation that leads toward its final stages. Stellar endings are not sudden events, but gradual changes unfolding over thousands of years, with each stage reshaping the star in new and sometimes unstable ways. The star at the center of the Boomerang Nebula has expanded into a red giant, its outer layers swelling outward while the core contracts and grows hotter. Helium fusion has started deep within, forming heavier elements like carbon and oxygen. At the same time, the star's outer envelope has stretched so far that it is only loosely held by gravity, delicately balanced against the outward push of radiation from below. In this fragile state, the star begins to lose mass, not slowly over millions of years, but more rapidly, releasing its outer layers into space at an unusually high rate. Over just a few thousand years, a significant portion of the star's mass can be carried away. This material streams outward as a powerful stellar wind, gently driven by the steady pressure of the star's own light. And perhaps there is another influence at work as well, a subtle asymmetry within the star, or the quiet presence of a companion star that remains hidden from direct view. This is where the deep cold begins to emerge. As the material streams outward into space, it expands very rapidly, and when gases expand in this way, they cool. It is a simple principle of thermodynamics, something you may have noticed if you have ever released compressed air and felt the chill of the escaping gas. In the Boomerang Nebula, this expansion takes place on a scale that is almost beyond imagination. The gas rushes outward at speeds greater than 600,000 kilometers per hour, far faster than the flows seen in most other nebulae. Such extraordinary speed leads to extraordinary cooling. The physics behind this process is gentle in its logic. Temperature is a measure of molecular motion. Close to the star, the gas is dense, and molecules move quickly, colliding often and sharing energy with one another. But as the gas spreads into the emptiness of space, each molecule finds more room, fewer neighbors, and fewer collisions. The expanding gas must work against the star's gravity as it moves outward, and that work requires energy. The energy is drawn from the motion of the molecules themselves. As they give up energy to fuel the expansion, their motion slows, and as their motion slows, the temperature falls. In most situations, this cooling would be balanced by warming from starlight or from the faint glow of the cosmic microwave background. Yet in the Boomerang Nebula, the expansion is so rapid and so extreme that cooling happens faster than any heating can keep up. The temperature drops dramatically, sinking even below the background temperature of the universe itself. The nebula becomes a small pocket of profound cold, resting within the comparatively gentle warmth of interstellar space. At a temperature of about 1 Kelvin, matter begins to behave in unusual and fascinating ways. The molecules in the expanding gas now move very slowly, only a small fraction of their typical speeds. Carbon monoxide molecules, which are common in the nebula, drift along at roughly 100 meters per second, far slower than they would at room temperature. It may still sound fast, but in terms of energy, it represents a profound quieting of motion. The molecules are nearing a realm where quantum effects start to matter more, where their wave-like nature gently influences how they move and interact. In such deep cold, molecules can form that would not survive in warmer environments. More complex carbon-containing molecules, long chains of atoms connected by delicate bonds, can assemble within the chilled gas. Dust grains also form more easily, as atoms that collide are more likely to cling together rather than bounce apart. The chemistry of extreme cold differs from that of warmer regions, allowing intricate molecular structures to arise, structures that need very low temperatures to remain stable. The Boomerang Nebula itself was first identified in 1980 by astronomers Keith Taylor and Mike Scarrett during a survey at the Anglo-Australian Observatory. They noticed its unusual shape and curious properties, but its extraordinary cold was not fully recognized until 1995. Astronomers Raghvendra Sahai and Lars Ake Nyman, using a sub-millimeter telescope in Chile, studied the radiation coming from the nebula and determined its temperature. What they discovered was remarkable, a temperature of just 1 Kelvin, colder than had seemed possible for any natural object in space. This finding raised an intriguing question. How could something in space be colder than the cosmic microwave background itself? The explanation involves not only the rapid expansion of gas, but also the shielding provided by dense clouds of gas and dust that help the nebula maintain its exceptional chill. The outer layers of the nebula gently absorb much of the cosmic background radiation before it can warm the innermost regions. Meanwhile, the expanding gas, doing work against gravity and against its own internal pressure, continues to cool even as the surrounding universe provides a faint bath of heat. For a short span in cosmic terms, perhaps 10,000 years, this nebula remains colder than the cosmos around it. Yet this deep cold does not last forever. The star at the center continues its slow transformation. In a few thousand more years, it will grow hot enough to ionize the surrounding gas, forming a true planetary nebula with softly glowing shells of illuminated material. As starlight pours energy into the gas, the temperature will rise. The extreme cold will fade, replaced by the gentle warmth of radiation. The Boomerang Nebula's remarkable chill is only a brief chapter in the long and graceful ending of a star's life. Observing the nebula requires careful instruments. Its faint light and wide structure make it difficult to see with small telescopes, though under very dark skies it may appear as a dim, ghost-like patch. Professional astronomers have explored it across many wavelengths of light, from radio waves to visible light to infrared. Each range reveals a different layer of its nature. Radio observations trace the distribution of molecular gas. Infrared images highlight dust and the remaining warmth closer to the star. Visible light photographs show starlight reflected from dust grains, outlining the nebula's distinctive form. In 1998, the Hubble Space Telescope captured an extraordinary image that revealed its structure in fine detail. At the center lies a bright region marking the dying star, surrounded by extended lobes of material flowing outward in opposite directions. These lobes appear textured and layered, hinting at multiple stages of mass being released over time. These layered patterns may reflect changes in the speed of the outflow over time. The overall form, once described simply as a boomerang, now appears more like an hourglass or the outstretched wings of a delicate cosmic butterfly. More recent studies using the Atacama Large Millimeter and Submillimeter Array, known as ALMA, have uncovered even greater complexity. The nebula contains a dense central region, roughly twice the size of our solar system, surrounded by a far larger envelope of expanding gas. Observations suggest that two stars orbit each other at the center, their gravitational interaction shaping the unusual structure and driving the intense loss of mass. A companion star could disturb the normal flow of stellar wind, creating the asymmetries we observe today. The molecules within the Boomerang Nebula are fascinating as well. At 1 Kelvin, carbon monoxide molecules emit faint radiation at specific millimeter wavelengths. By studying this delicate signal, astronomers can determine the temperature and motion of the gas. They can map how temperature changes throughout the nebula and have found that the coldest regions are not at the center, but in the fast-moving lobes, where expansion is strongest and cooling most dramatic. In reflecting on the Boomerang Nebula, we are observing a natural laboratory for extreme physics. In the quiet spaces between stars, conditions arise that approach those scientists work hard to reproduce in advanced laboratories on Earth. The nebula reminds us that the universe, in its vast range of environments, can produce nearly anything that the laws of physics allow. Under the right conditions, a fading star, rapid mass loss, and the right balance of density and composition, temperatures within a single degree of absolute zero can appear naturally as part of the cosmic story. This deep cosmic cold will not last forever. Even now, the nebula is slowly changing. The central star continues its quiet transformation, and the great clouds of gas drift farther into space, spreading out, thinning, and gradually warming as they mix with the surrounding interstellar medium. In a relatively short cosmic time, the Boomerang Nebula will no longer hold its record. It will become a more typical planetary nebula, still beautiful, still mysterious, but no longer defined by such extraordinary cold. Yet for this brief moment in the long history of the universe, this fading star has created the coldest natural place we know. There is something poetic in that. Not cold as an ending, but cold as part of a transformation. A star shedding its outer layers, releasing matter into the vastness, shaping a temporary state that will one day pass. The universe is always moving from one condition to another, and even extreme cold is just a step along that path. In that quiet transition, we can sense a gentle reflection of change itself. States that feel permanent are often only pauses in a much longer story. The Boomerang Nebula reminds us that even the most extreme conditions are part of a flow, a slow and graceful evolution written across space and time. And while nature creates remarkable cold in distant space, human curiosity has found ways to go even further. Quantum mechanics and ultra-cold matter. In a laboratory at the Massachusetts Institute of Technology, scientists have created temperatures even lower than those in the Boomerang Nebula. Using carefully controlled lasers and magnetic fields, they cooled atoms to just a few hundred picokelvin, only trillionths of a degree above absolute zero. This is colder than anywhere naturally known in space, making it the coldest matter ever produced in the universe so far. At such temperatures, the familiar rules of everyday physics begin to soften, and the strange, quiet world of quantum mechanics becomes easier to see. To understand this journey into extreme cold, we begin with a simple idea. Temperature is motion. The warmer something is, the faster its particles move. So to create deep cold, scientists must gently slow that motion down. But atoms cannot simply be grabbed and held still. The laws of quantum physics do not allow that. If you try to pin down an atom's position too precisely, its motion becomes wildly uncertain. This is known as the uncertainty principle, and it sets a fundamental limit on how still matter can become. Because of this, researchers use indirect and very elegant methods to remove energy from atoms. One of the most important breakthroughs came with laser cooling. At first, this sounds surprising. We usually think of lasers as adding energy, not taking it away. But when tuned with incredible precision, laser light can actually slow atoms down. Atoms can absorb tiny packets of light, called photons, but only when the light has exactly the right energy. Each time an atom absorbs a photon, it receives a small push in the direction the light was traveling. Scientists arrange laser beams so that atoms moving in any direction are more likely to absorb light. Imagine a cloud of atoms drifting in a near-perfect vacuum. They move randomly, in all directions. Now, soft laser light shines from opposite sides. Because of the Doppler effect, atoms moving toward a beam see the light slightly shifted in frequency, making absorption more likely. When they absorb that light, they receive a tiny recoil that slows them down. Atoms moving away are less affected. Over many repeated interactions, the overall motion of the atoms decreases. Step by step, their temperature falls, and the cloud grows quieter and calmer. Atoms drifting away from the light are affected less, while those moving toward it are gently slowed again and again. With every cycle of absorbing and releasing light, a tiny bit of motion is removed. Gradually, the swarm of atoms calms, their restless movement fading, their temperature falling closer and closer to absolute zero. Scientists arrange 6 laser beams from opposite directions so the atoms are cooled from all sides at once. The effect is often compared to moving through thick syrup, even though the atoms are actually floating in empty space, slowed only by carefully tuned light. This method, known as laser cooling, can reach temperatures just a few millionths of a degree above absolute zero, an extraordinary achievement in modern physics. Yet, even this is only part of the journey toward the coldest temperatures ever created. To go further, researchers use evaporative cooling, a process similar to how a warm drink cools as its hottest molecules escape into the air. In the lab, atoms are held in magnetic or optical traps, and the most energetic ones are allowed to slip away. As they leave, they carry excess energy with them, and the remaining atoms settle into an even colder, quieter state. By combining these techniques, scientists reach the nanokelvin range, billionths of a degree above absolute zero, conditions colder than deep space itself. At these extreme temperatures, matter begins to change in a profound and beautiful way. The atoms no longer behave like separate particles bouncing around. Instead, they enter a shared quantum state known as a Bose-Einstein condensate, a form of matter first predicted in the early 20th century and finally observed decades later. In this strange state, the boundary between individual atoms begins to blur, and the quiet rules of quantum physics start to shape reality in ways we can almost see. This remarkable transformation happens because, in the quantum world, identical particles are truly indistinguishable. One atom cannot be labeled or tracked as separate from another of the same type. This simple fact leads to deep consequences. Particles are grouped into two families, bosons and fermions, based on a property called spin. Bosons have an unusual ability. Many of them can share the exact same quantum state at the same time. At ordinary temperatures, this does not matter much, because constant motion keeps atoms spread across many different energy states. But as the temperature falls and motion slows, their wave-like nature becomes more important. Each atom is described not just as a tiny point, but as a spreading wave of probability. As the atoms grow colder, these waves expand. Eventually, neighboring waves begin to overlap, and the atoms can no longer be treated as separate objects. They blend into a single collective state, described by one shared wave function. This is the heart of a Bose-Einstein condensate, where thousands or even millions of atoms move together as if they were one gentle quantum wave. They still possess a trace of motion, because the uncertainty principle does not allow perfect stillness, but they exist in the lowest energy state nature permits. In this calm and delicate condition, matter reveals behaviors normally hidden by warmth and chaos. The study of these ultra-cold states helps scientists explore quantum physics, the fundamental laws that shape the universe from the smallest scales to the vast cold reaches of deep space. In this state, the condensate behaves like a single, flowing matter wave. It can create interference patterns, tunnel through barriers, and display behaviors usually reserved for the tiniest particles, now visible on a scale large enough to measure directly. When scientists gently spin a condensate, it does not swirl in any random way. Instead, tiny quantized vortices appear, miniature whirlpools where rotation can take only specific values. These vortices arrange themselves into delicate, orderly patterns, like a lattice forming in a quiet quantum fluid. Using finely shaped beams of light, researchers can sculpt the condensate, dividing it, guiding it, and even letting different parts overlap so it interferes with itself. One of the most beautiful experiments happens when the trap holding the atoms is turned off. The condensate begins to expand, but not like an ordinary gas. It spreads unevenly, faster in some directions, slower in others, revealing the shape of its inner quantum state. By studying this gentle expansion, physicists can read the hidden motion of the atoms before release, gaining a rare glimpse into a living quantum system. These ultra-cold clouds have even been used to model cosmic events. By rapidly changing their conditions, scientists recreate effects similar to those believed to have happened in the early universe, allowing them to explore how structure and order can emerge from extreme physical transitions. Experiments at temperatures just billionths of a degree above absolute zero are helping us understand processes linked to the hottest moments in cosmic history. It is a quiet reminder that the very cold and the very hot are deeply connected in the laws of physics. Another unusual state appears when particles called fermions are cooled to extreme lows. Fermions normally refuse to share the same quantum state, a rule known as the Pauli exclusion principle, which shapes the structure of atoms and the stability of matter itself. But when conditions are cold enough, fermions can pair together. Each pair then behaves like a boson, which allows them to gather into a shared quantum state. This pairing is closely related to the process behind superconductivity, where electricity flows without resistance. In laboratories, scientists create these fermionic condensates by cooling special atomic gases and carefully adjusting magnetic fields so the atoms attract and form pairs. The result is a superfluid made of paired particles, flowing without friction in a way that feels almost dreamlike compared to ordinary liquids. Reaching such extreme cold is difficult on Earth because gravity constantly pulls the atoms downward, limiting how long they can be observed. For this reason, some of the coldest experiments have taken place in orbit, where microgravity allows atoms to drift gently for longer periods, giving researchers more time to study the calm and delicate behavior of matter near the lowest temperatures nature allows. High above Earth, orbiting in quiet darkness, a special laboratory continues this journey into extreme cold. The Cold Atom Laboratory aboard the International Space Station has created Bose-Einstein condensates in microgravity, cooling atoms to temperatures lower than almost anywhere else ever achieved. In weightlessness, atoms can be handled more gently, held with weaker traps, and allowed to drift with almost no disturbance. This calm environment lets scientists lower the temperature even further until atomic motion becomes so small that quantum behavior completely takes over. At these temperatures, the usual idea of a tiny particle moving along a clear path no longer works. Each atom is better described as a soft quantum wave spread out in space. Its wavelength becomes large compared to the distance between atoms, so the waves overlap, blend, and form a single shared quantum state. Motion slows to such an extent that from our perspective the atoms seem almost frozen in time, drifting at only millimeters per second. Their position is no longer a sharp point but a cloud of probability, a gentle blur defined by the rules of quantum mechanics. When millions of atoms share this same state, they create a visible quantum object, something balanced between the strange microscopic world and the solid everyday world we know. In this delicate regime, researchers explore physics in its purest and quietest form, where the noise of heat no longer hides the deeper patterns of reality. These ultra-cold systems are more than scientific curiosities. They act as simple, controllable models for much more complex parts of the universe. By studying them, scientists gain insight into the behavior of electrons inside materials, the dense matter inside neutron stars, and even processes that shaped the early cosmos. They also lead to practical tools, including extremely precise atomic clocks, advanced quantum computers, and sensors sensitive enough to measure tiny changes in gravity or fundamental physical constants. Yet beyond technology and theory, there is something deeply calming about the pursuit of absolute zero. It is the search for the quietest state matter can reach, the lowest energy condition allowed by nature. As we approach that limit, we do not find emptiness. Instead, we discover new forms of order, new states of matter, and behaviors that only appear when almost all motion has faded away. Curiously, the coldest known matter does not exist in deep space, but in carefully designed laboratories and orbiting stations. The vast universe, for all its size and extremes, does not easily create such profound cold on its own. It takes knowledge, patience, and careful control to remove energy step by step until matter settles into its quantum ground state. In doing so, we reveal a gentle truth. When the noise of heat is gone, the universe does not fall silent. It begins to whisper its most subtle secrets. Between the stars there is a kind of cold that feels like emptiness. If you could drift far from any sun, deep in interstellar space, the temperature would settle near the natural background warmth of the universe itself, about 3 Kelvin. This faint heat comes from the cosmic microwave background, the gentle afterglow of the Big Bang that still fills all of space. It is not absolute zero, but it is colder than anything we naturally experience on Earth. In some regions, the temperature drops even further, approaching the deep cold found in rare places like the Boomerang Nebula. Interstellar space is not completely empty. Matter exists between the stars, though in densities so low that we would call it a vacuum by earthly standards. On average, there may be only a single atom in a cubic centimeter. Yet space is so vast that even this thin material gathers into enormous clouds over great distances. These clouds drift in darkness, shielded from starlight, and their temperatures can fall to 10 Kelvin or even lower. They are known as dark molecular clouds, immense regions of gas and dust scattered throughout the galaxy. From Earth they appear as dark patches against the glow of distant stars, where light is absorbed by the material within. Some stretch across hundreds of light years and contain enough mass to form millions of suns, yet the matter inside them remains incredibly diffuse, quieter and emptier than any laboratory vacuum. The cold inside molecular clouds comes from their isolation and their composition. These regions are made mostly of hydrogen and helium, along with trace elements, complex molecules, and tiny dust grains. Those dust grains, though smaller than a speck you could ever see, play a crucial role. They absorb starlight and ultraviolet radiation, preventing warmth from reaching deep into the cloud. The outer layers act like a blanket, protecting the interior and creating vast zones of darkness. In these hidden regions, the only steady warmth comes from the faint cosmic background and the occasional passing cosmic ray. As a result, temperatures fall to between 10 and 20 Kelvin. On Earth, most gases would freeze at such temperatures, but in the near vacuum of space the pressure is too low for that to happen. The gas remains a gas, though the molecules drift slowly, carrying very little energy. In this gentle cold, chemistry behaves in unusual ways. On Earth, chemical reactions usually need heat to push molecules over energy barriers. But in molecular clouds, reactions can happen through quantum tunneling, where particles pass through barriers they could not cross in classical physics. Reactions also occur on the surfaces of dust grains, where atoms and molecules meet, stick, and combine. In this quiet darkness, under extreme cold, the basic ingredients of stars and planets begin their slow and patient transformation. Dust grains drift through these dark clouds like tiny floating islands, and on their surfaces a quiet kind of chemistry unfolds. When a lone hydrogen atom glides through space and settles onto a grain, it is held gently by weak forces, resting there in the cold. Another hydrogen atom may arrive sometime later, wandering across the grain's surface until it meets the first, and together they join to form a hydrogen molecule. This simple meeting is one of the most important processes in the universe, because molecular hydrogen does not form easily through direct collisions in such cold, thin gas. And yet it is the most abundant molecule in space. Almost all of it is created on the surfaces of these microscopic grains inside cold molecular clouds. From this humble beginning, more complex chemistry slowly grows. Carbon monoxide, water, ammonia, methanol, and gradually larger organic molecules assemble piece by piece on grain surfaces. Some of these remain frozen in place, forming delicate icy layers that coat the dust like frost. Others return to the gas when a grain is gently warmed by nearby radiation. Over millions of years, this slow and patient process builds an unexpected richness, with more than 200 different molecules now identified in interstellar space, many of them organic and built from chains and rings of carbon. The coldest pockets inside these clouds are known as dense cores, compact regions where the number of particles rises to thousands or even tens of thousands per cubic centimeter. By Earth standards, this is still an extreme vacuum, yet it is dense enough for gravity to begin its quiet work. In these sheltered places, temperatures can fall below 10 Kelvin, approaching the deep cold seen in rare objects like the Boomerang Nebula, though reached here through stillness rather than dramatic expansion. Within these dense cores, the story of star birth begins. When a core gathers enough mass and becomes sufficiently concentrated, gravity slowly overcomes the gentle pressure of the gas, and collapse begins. At first, this change is almost imperceptible, unfolding over hundreds of thousands of years. But as the core contracts, it also warms, and the process gradually accelerates. In time, the center grows hot and dense enough for nuclear fusion to ignite, and a new star is born, turning a dark and frozen cradle into a source of light and warmth. Before that awakening, however, these cores are among the coldest natural environments in the galaxy. Temperatures of 6 or 7 Kelvin have been measured in some regions, where shielding from starlight is nearly complete, densities remain low, and energy is radiated away with great efficiency. In certain small pockets, temperatures can even dip locally below the cosmic microwave background for a time, creating natural cold traps where matter gathers and cools while gravity patiently draws it inward. To study these hidden places, astronomers must look beyond visible light, which cannot pass through the dust. Instead, they observe longer wavelengths such as infrared, submillimeter, and radio. Molecules like carbon monoxide emit faint radiation at millimeter wavelengths, and by examining the strength and shape of these signals, scientists can estimate the temperature and motion of the gas. Different molecules shine at different wavelengths, each revealing conditions in slightly different parts of the cloud. Despite their deep cold, molecular clouds are not completely still. They are filled with gentle turbulence, stirred by magnetic fields, winds from young stars, and the slow collapse of smaller regions within the larger structure. These internal motions create variations in speed that can rival or exceed the random thermal motion of the molecules themselves, adding a subtle restlessness to an otherwise quiet and frozen realm. Imagine floating in a molecular cloud, vast and dark, where the thermal energy of individual molecules is almost imperceptible. The cloud moves and churns with streams of gas, collapsing cores, rotating structures, and expanding shells from distant stellar explosions, carrying energy in their motion but remaining quietly cold. Weak magnetic fields guide charged particles and ionized gas, offering gentle resistance to gravitational collapse and subtly steering cosmic rays that bring tiny amounts of warmth. These cosmic rays, mostly protons racing near light speed, strike molecules and deposit energy, a faint but persistent heat that prevents the cloud from becoming infinitely cold. Even as this gentle energy flows, the cloud's interior remains profoundly quiet, molecules drifting slowly through the darkness, their motion measured only in the tiniest fractions of speed, allowing the universe's subtle rhythms to unfold. In the densest, most shielded regions, the cloud grows almost motionless. Cosmic rays are scattered by the outer layers, and radiative cooling from molecules like carbon monoxide allows temperatures to drop to around 10 Kelvin, creating a natural stillness that is rarely disturbed. The cold settles into a quiet balance, a soft limit where the cloud neither warms nor cools further, forming an environment so empty and delicate that a single step would meet only one drifting molecule. Darkness is complete, starlight unable to penetrate, and the cold wraps everything in a silent embrace. Yet within this emptiness, molecules drift slowly, forming invisible currents that speak of the subtle chemistry of the cosmos. Walking through this cloud in your mind, you feel the stillness, the profound quiet, the gentle isolation, a reminder of the universe's vast and serene spaces. Imagine drifting through a molecular cloud where carbon monoxide, ammonia, water ice, and complex organic molecules slowly gather on tiny dust grains. Around you, the faint hum of the cosmic microwave background flows like a gentle whisper, photons left over from the Big Bang, providing a subtle warmth that fills the emptiness. These clouds are patient, existing for millions of years, quietly collecting mass, cooling in the darkness, preparing for the eventual collapse that will ignite new stars and planets. Their cold is not final but a pause, a stillness before transformation, a quiet waiting where matter and gravity gather in anticipation of light and warmth. Every atom in our bodies, every element in our solar system, was once part of such a cloud, drifting through shadowed spaces, shaped by the slow chemistry of cold and isolation. 4.5 billion years ago, a cloud in this region of the galaxy collapsed to form the Sun and planets, including Earth. The chill of that ancient cloud has long since become the warmth of our world, but its memory lingers in the chemistry of rocks, in the isotopes that tell the story of time, in the very fact of our existence. All around us, space itself holds a baseline cold, the cosmic microwave background, a faint warmth that permeates every corner of the universe. At just 2.725 Kelvin, it is a whisper above absolute zero, unavoidable and fundamental. This radiation is not from anything present now, but a remnant, light that has traveled nearly 14 billion years from the universe's earliest moments, cooled by cosmic expansion from the fiery heat of creation to the delicate glow we sense today. The CMB confirms the Big Bang, revealing the universe's age, composition, and structure, and defining the natural cold that exists in empty space, far from stars or heat sources. At the universe's birth, everything was a plasma of particles moving at nearly the speed of light, photons trapped in endless scattering with electrons and protons. For nearly 400,000 years, light could not escape. Then, as expansion continued and temperatures fell below 3,000 Kelvin, electrons and protons combined into neutral hydrogen, allowing photons to travel freely. Space became transparent, and that light, carrying the first stories of the cosmos, has been journeying across the universe ever since, a gentle reminder of the stillness and quiet that underlies all things. The light we see from the cosmic microwave background has traveled nearly 14 billion years, stretched by the expansion of the universe, and cooled from 3,000 Kelvin to the gentle 2.7 Kelvin we observe today. When we look at this ancient glow, we are peering back to a moment when the universe first became transparent, a surface of last scattering where photons began their long journey across the cosmos. Every direction we turn, this primordial light reaches us, a fossil from the universe's infancy, carrying whispers of conditions that existed just after the Big Bang. Predicted decades before its discovery, the CMB was finally detected in 1964 by Arno Penzias and Robert Wilson, who found a faint, persistent microwave signal coming uniformly from all directions, confirming what theory had foretold. Its temperature is astonishingly uniform, matching to within 1 part in 100,000 across the sky, a cosmic harmony that invites wonder and reflection. How could regions of space so distant, never in causal contact, share such precise balance? The answer lies in cosmic inflation, a brief, breathtaking expansion in the first moments of the universe, stretching a small, thermally balanced patch into the vast cosmos we observe today. Even in its calm, the CMB carries tiny fluctuations, minute variations in temperature, mere parts in 100,000. Yet these subtle differences are the seeds of everything: the galaxies, stars, and planets we know. Denser regions gathered matter under gravity, forming clusters and galaxies, while slightly emptier regions became voids, vast cosmic spaces with few stars. Mapping these fluctuations with satellites like COBE, WMAP, and Planck has allowed us to read the universe's story with extraordinary precision, revealing its age, shape, and composition. In contemplating this faint, omnipresent glow, we sense the quiet patience of the cosmos, a gentle reminder of the vast scales of time and space, the stillness between creation and structure, the subtle interplay of order emerging from the earliest moments of everything we know. The temperature fluctuations in the cosmic microwave background are not random. They trace patterns from sound waves that traveled through the primordial plasma before the universe became transparent. These waves created regions of compression and rarefaction, frozen in place when light first escaped, revealing a cosmic fingerprint. By studying these subtle oscillations, cosmologists can understand the geometry of space itself, showing that the universe is nearly flat. Among these patterns is the intriguing cold spot, a region slightly cooler than expected, barely noticeable but significant. Its origin is still debated, from possible supervoids to more exotic explanations. The CMB defines a natural temperature scale for the universe, guiding the cooling of objects in empty space toward its faint, omnipresent glow. While the universe expands, this radiation cools slowly, a gentle reminder of the cosmos' long, patient evolution. Shortly after recombination, the CMB glowed at around 3,000 Kelvin, visibly radiant. Over billions of years, as the universe expanded, its temperature dropped to the 2.7 Kelvin we observe today. Looking at it is like peering into the infancy of the cosmos, observing light from the edges of the observable universe and uncovering conditions nearly 14 billion years ago. Measuring this faint signal requires careful separation from foreground emissions of our galaxy, dust, and free electrons. Instruments observe multiple frequencies, distinguishing the primordial whisper from local sources. The CMB has the most perfect blackbody spectrum ever measured, showing that the early universe was in remarkable thermal balance. It carries information about the primordial fluctuations that seeded galaxies, stars, and planets, guiding our understanding of cosmic history and the evolution of structure on the largest scales. Scientists are searching for subtle patterns in the cosmic microwave background called B-mode polarization, faint imprints of gravitational waves from cosmic inflation. Detecting them would reveal the earliest moments of the universe and physics at energies far beyond our laboratories. The CMB also defines the natural cold of space, setting a baseline temperature of 2.7 Kelvin. Any object left alone will gradually equilibrate to this faint glow, and cooling below it requires extraordinary conditions, like the rapid expansion of the Boomerang Nebula. That nebula's temperature of 1 Kelvin is remarkable, colder than the universe itself naturally allows. In contemplating the CMB, we are contemplating the universe as a whole, its history written in light. Its thermal rhythm still echoing billions of years after the Big Bang. 2.7 Kelvin is far colder than anything we experience on Earth, yet it carries the warmth of creation, a soft, enduring glow slowly fading toward absolute zero, reminding us of the universe's infinite patience and its quiet, steady unfolding. Far beyond the inner solar system, past the asteroid belt, lie worlds locked in perpetual winter. The outer planets and their moons orbit so far from the sun that its warmth is negligible, their surfaces frozen into landscapes of ice and frost that never melt. Among them, Neptune stands out, orbiting 30 times farther from the sun than Earth. At this distance, the sun is just a bright star, giving only a tiny fraction of the warmth we feel. Neptune's upper atmosphere, rich in hydrogen, helium, and traces of methane, cools to 50 to 60 Kelvin, cold enough to freeze methane into clouds that color the planet blue. Yet Neptune radiates more energy than it receives from the sun, a faint internal heat left over from its formation. The coldest parts lie in the upper atmosphere, untouched by this internal warmth and beyond the sun's reach. Uranus, closer at 19 astronomical units, is even colder, emitting almost no excess heat. Its icy envelope drifts in extreme cold, a quiet, frozen world moving through the vast, dim reaches of the solar system. These outer planets remind us of the persistent cold that exists naturally in space, a temperature shaped by distance, composition, and time, a slow and steady rhythm stretching across billions of kilometers of darkness. Uranus's upper atmosphere drops to 49 Kelvin, colder than Neptune's, making it the coldest planetary atmosphere in the solar system. Scientists are still unraveling why Uranus lacks internal heat, one idea being a massive ancient collision that tilted the planet and allowed it to cool more efficiently. Yet the coldest places aren't on the planets themselves, but on their moons and in permanently shadowed regions untouched by sunlight. Triton, Neptune's largest moon, is one of the coldest surfaces, hovering around 38 Kelvin. Its frozen nitrogen, methane, and carbon dioxide, combined with a high albedo reflecting 70% of incoming sunlight, prevents significant warming. Triton also has a tenuous nitrogen atmosphere, and the seasonal sublimation and condensation of nitrogen ice creates a cooling effect similar to evaporative cooling on Earth, keeping its surface uniformly frigid. The extreme cold allows unique geological features to exist. Nitrogen geysers erupt from below, carrying dark organic material across icy plains, a slow and quiet choreography of chemistry and physics at the edge of the solar system. Even though Triton's geysers are barely warmer than the surrounding ice, they reveal active geology on a world colder than any natural place on Earth. Pluto, orbiting about 40 astronomical units from the Sun, ranges from 33 to 55 Kelvin. Its nitrogen ice sublimates into a thin atmosphere at perihelion and refreezes when farther away, cycling over centuries. Pluto's surface is a frozen mosaic of nitrogen plains, water ice mountains, and patches of methane and carbon monoxide, as revealed by New Horizons in 2015. The cold preserves ancient features while slowly reshaping others through sublimation and deposition. Even closer to the Sun, permanently shadowed craters near the poles of Mercury and the Moon harbor extreme cold. Shielded from sunlight by crater walls, temperatures can fall below 40 Kelvin, a stark contrast to the blazing heat just beyond their edges. In these silent shadows, the solar system keeps its coldest secrets, quiet and persistent, a frozen rhythm of light and dark, warmth and ice, stretching across billions of kilometers of space. Permanently shadowed craters act as cold traps, collecting volatile materials delivered by comets and asteroids over billions of years. Water ice has been detected in these regions along with other frozen compounds, persisting because temperatures never rise high enough for sublimation. On the Moon, some shadowed craters near the South Pole reach 25 Kelvin, colder than Pluto's surface. Even colder regions may exist on distant moons of Saturn and Uranus, largely unexplored, small frozen worlds drifting in the outer solar system's permanent cold. Enceladus, one of Saturn's moons, shows a contrast. Its average surface temperature is about 75 Kelvin, warmed by internal tidal heating caused by Saturn's gravity. Cracks in the icy shell flex and generate frictional heat, creating geysers near the South Pole that erupt water vapor from subsurface oceans. Here, temperatures can exceed 200 Kelvin, enough for liquid water beneath the ice. Yet the majority of Enceladus remains frozen, and areas far from the geologically active pole sit around 70 Kelvin, a quiet reminder of the outer solar system's frozen vastness. The contrast between warm, active regions and the cold, inactive ones illustrates how local heating can create pockets of warmth. Yet most surfaces in the outer solar system remain below 100 Kelvin, freezing nearly any earthly substance. Atmospheres, where present, behave in fascinating ways at these low temperatures. Titan, Saturn's largest moon, has a dense nitrogen atmosphere with a surface pressure 50% greater than Earth's, but a surface temperature of 94 Kelvin, cold enough for liquid methane to exist. Titan experiences a methane cycle like Earth's water cycle, with lakes, seas, rain, and rivers of methane sculpting the landscape, depositing sediments, all at a temperature where water is as hard as rock. Cold slows geological processes, but does not stop them. Surfaces evolve through sublimation, deposition, and the slow creep of ice. Atmospheres exist and change. Each new mission and observation continues to reveal surprises, showing that cold does not equal lifelessness. Future missions like Europa Clipper and Dragonfly will explore Europa and Titan, offering insights into chemistry and physics at extreme cold, and potentially guiding our search for life in frozen environments across the universe. Life, as we know it, requires liquid water, and liquid water requires temperatures above 273 Kelvin at Earth's atmospheric pressure. Yet in subsurface oceans of icy moons, higher pressures and dissolved salts or ammonia can lower the freezing point, allowing liquid water to exist well below this. Life, if present, might adapt in ways we have not imagined, using different biochemistry, energy sources, or strategies to sustain metabolism in the near-freezing darkness beneath kilometers of ice. The cold of the outer solar system is not as extreme as molecular clouds or the Boomerang Nebula, but it is profound by terrestrial standards. A world of perpetual winter, frozen landscapes billions of years old, and atmospheres composed of gases that would instantly liquefy or freeze on Earth. These worlds remind us that cold is the universe's natural state. Warmth, the temperatures we take for granted on Earth, is the exception, maintained by a star's proximity and our planet's unique atmosphere. In contemplating these frozen realms, we sense isolation. They orbit in darkness, untouched by liquid water or familiar life, but they are connected to us through the laws of physics, the chemistry forged in ancient stars, and the shared story of solar system formation. They are chapters in the cosmic tale of matter across temperatures ranging from the coldest cold to the hottest heat. Brown dwarfs occupy the space between the largest planets and the smallest stars, massive enough to form like stars, but not massive enough to sustain hydrogen fusion in their cores. Often called failed stars, they glow with dim heat from gravitational contraction and residual formation energy, but never ignite nuclear fires like true stars. The coldest among them are only slightly warmer than the planets they resemble, with temperatures where water vapor can condense into clouds, blurring the line between star and planet. Brown dwarfs form like stars. A gas and dust cloud collapses under gravity, heating as it contracts. But with less than 8% the mass of the Sun, the core never reaches the temperature needed for sustained hydrogen fusion. Some of the more massive brown dwarfs fuse deuterium briefly during youth, but deuterium is rare, comprising only 20 parts per million of normal hydrogen, and this phase lasts only a few million years. Afterward, the brown dwarf cools, radiating heat into space, growing dimmer and colder over billions of years. The coldest brown dwarfs belong to the Y spectral class, with temperatures below 500 Kelvin, and the coolest examples nearing or even below 300 Kelvin, roughly room temperature. At these gentle, fading temperatures, a brown dwarf becomes cool enough for water clouds to form, and it gives off most of its light in the soft glow of infrared, barely shining at all in visible light. One of the coldest known brown dwarfs, Y08550714, drifts only about 7 light-years from Earth. Its temperature is estimated to be between 250 and 300 Kelvin, making it one of the chilliest substellar objects ever discovered. In this quiet range of cold, water no longer floats as vapor, but gathers as tiny ice crystals, suspended in the atmosphere and forming clouds that resemble those on Earth, though made of frozen particles instead of liquid droplets. The air there likely holds ammonia and methane as well, creating a rich and layered chemistry that feels more like Jupiter than a true star. Discoveries like this became possible thanks to the WISE Space Telescope, which scanned the sky in infrared light, revealing objects too cool and dim to be seen from the ground. Brown dwarfs are naturally faint, and the coldest ones shine almost entirely in mid-infrared wavelengths that Earth's atmosphere blocks, so only space-based eyes can truly find them. WISE uncovered thousands of brown dwarf candidates, including many belonging to the ultra-cool Y class, showing us a hidden population of dark, quiet worlds between stars. Over time, every brown dwarf slowly cools. A young one, still warm from its formation, might glow at 2000 Kelvin or more. Across millions of years it drifts downward through 1000 Kelvin, then 500, and eventually toward temperatures more like those of planets. Heavier brown dwarfs cool more slowly, holding onto their heat longer as they gradually release the energy stored deep within. The oldest and lightest brown dwarfs in our galaxy may have cooled to below 200 Kelvin. Though such faint objects are extremely difficult to detect, at temperatures close to a comfortable room, a brown dwarf begins to resemble a giant planet. Both are made mostly of hydrogen and helium. Both carry atmospheric temperatures in the low hundreds of Kelvin, and both give off only a dim infrared glow. The key difference lies in how they are born. Brown dwarfs form when clouds of gas collapse on their own, much like stars, while planets grow inside disks that circle young stars. Yet at masses around 10 to 15 times that of Jupiter, this boundary softens, and the formation paths may overlap. The atmosphere of a cold brown dwarf is a layered and ever-changing place. Below 500 Kelvin, different substances can condense into clouds. Water clouds appear near 300 Kelvin. Ammonia ice may form at even lower temperatures. Beneath 200 Kelvin, methane could begin to condense, though no brown dwarf that cold has yet been clearly observed. These atmospheres stack into layers, with each cloud deck forming at the altitude where its chemicals can turn from gas to ice. Even in the deep cold, these worlds are not still. Observations in infrared light reveal changing brightness in Y-class brown dwarfs over hours or days. This gentle flickering likely comes from atmospheric features slowly rotating into and out of view as the object spins. Vast storms, openings in cloud layers, or shifting temperature patterns driven by winds may all play a role, creating a calm but dynamic weather system on these dark, drifting worlds of the cosmos. Even on worlds only a little warmer than a mild summer day on Earth, weather can still exist, reminding us that atmospheric motion is not limited to hot planets. By studying the light from brown dwarfs, scientists can read the chemical fingerprints in their atmospheres. These spectra reveal the presence of water vapor, methane, ammonia, and other molecules drifting through their cold skies. In the chilliest brown dwarfs, the signals from water grow especially strong, showing that water becomes one of the main ingredients of the atmosphere. As temperatures fall, methane becomes more common as well, naturally replacing carbon monoxide in cooler conditions. Another fascinating feature of brown dwarfs is their magnetic fields. Even though they are faint and cool, many of them generate magnetic fields as strong as the sun's. Deep inside, moving layers of electrically conducting material create currents, and those currents build magnetic fields, much like in stars and planets. These fields can capture charged particles and form vast magnetic bubbles around the object. In some cases, this may even create auroras, though they would glow mainly in radio waves rather than visible light. The coldest brown dwarfs may also experience familiar kinds of weather in very unfamiliar forms. If water clouds are present, they could produce precipitation, gentle falls of ice particles drifting through a thick hydrogen and helium atmosphere. These frozen droplets would descend through chilly layers, then slowly turn back into vapor deeper down where temperatures rise again. This quiet cycle of condensation and evaporation mirrors the water cycle on Earth, but it unfolds in the atmosphere of a dim, failed star floating alone in space. Brown dwarfs help us understand both stars and planets, because they exist in the wide space between these two families of objects. By observing them, We gain insight into atmospheric behavior, internal structure, cooling over time, and the physics of bodies that are too small to shine like stars yet too massive to be ordinary planets. They also act as natural laboratories for studying conditions similar to those on giant exoplanets orbiting distant stars, worlds that are too faint and far away to examine closely, but may share much in common with cold brown dwarfs. The search for these quiet objects continues with ever more sensitive instruments. The James Webb Space Telescope, with its powerful ability to see infrared light, can detect brown dwarfs cooler than any found before. Future sky surveys may uncover objects with temperatures below 200 Kelvin, blurring the line between brown dwarf and planet even further. Each discovery challenges how we classify cosmic objects and deepens our understanding of how they form and change over time. In the vast scale of cosmic temperatures, even the coldest brown dwarfs are not truly cold. At around 300 Kelvin, they are still much warmer than the faint afterglow of the Big Bang and warmer than some of the coldest regions of space. Yet they occupy a beautiful middle ground where star-like bodies cool to planet-like temperatures, where the physics of stars gently gives way to the physics of planets, and where nature resists being placed into neat categories. Brown dwarfs quietly remind us that the universe is filled with in-between worlds, objects that sit softly between definitions, inviting us to keep exploring. They are not quite stars and not quite planets, but something in between, showing us that the universe does not draw hard lines between its creations. As brown dwarfs slowly cool from the warmth of their birth toward a long, quiet balance with the cold of space, they follow a path that much of matter may one day share, a gradual journey from heat to deep cold that unfolds over billions of years. Now imagine a different kind of world, a planet that no longer circles a star. Cast out by powerful gravitational encounters, it wanders through interstellar space with no sun to warm it. These are rogue planets, also called free-floating planets, drifting alone through the galaxy. Without starlight, they steadily cool, moving closer and closer to the faint temperature of the cosmic background radiation, and they may become some of the coldest large objects in existence. Rogue planets can arise in two main ways. Some begin like ordinary planets, forming an orbit around a young star, but later they are thrown out by close encounters with other planets or passing stars. Computer simulations show that this kind of ejection is common in the early, chaotic stages of planetary systems, when worlds shift orbits and tug strongly on one another. Large planets with masses like Jupiter are especially effective at flinging smaller neighbors out into the dark between stars. Other rogue planets may form on their own, much like brown dwarfs, from gas clouds too small to ignite as stars. These objects would be planets in mass, but star-like in origin, another example of how nature blurs the categories we try to impose. Observations of star-forming regions suggest that such free-floating planetary mass objects really do exist, quietly roaming the galaxy without a central sun. Whether these lonely worlds formed by themselves or were expelled from young planetary systems is often hard to determine. Far from any star, a rogue planet must rely only on its own internal heat. Leftover warmth from its formation slowly leaks away into space. At the same time, the gentle decay of radioactive elements deep inside provides a small but steady source of heat. In more massive planets, slow gravitational contraction and cooling of the interior can also release energy for billions of years. Even so, these heat sources are limited, and over immense spans of time the planet cools toward the temperature of its surroundings. How cold a rogue planet becomes depends on its size, age, and makeup. A Jupiter-sized planet ejected while still young might hold enough internal warmth to stay at several hundred Kelvin for millions of years. But as it ages, it cools. After a billion years, such a gas giant might drop to roughly 50 to 100 Kelvin. After 10 billion years, it could come close to the temperature of the cosmic background, only a few degrees above absolute zero, though small amounts of internal heating may keep it slightly warmer. Smaller rogue planets cool faster because they lose heat more easily. An Earth-sized world cast into interstellar space would freeze solid in just a few million years. Its atmosphere could condense onto the surface or slowly escape into space. Any oceans would freeze from the top downward, the ice thickening over time until the entire ocean turns solid. In the end, even the remaining gases might freeze out, leaving a silent sphere of ice drifting through the darkness. Yet for larger planets, the story may not end there, and hidden warmth could linger far below their frozen surfaces. If a rogue planet retains enough internal heat, and if it has a thick atmosphere or ice shell, liquid water could survive far below the frozen surface even without any starlight. The outer ice would act like a blanket, holding in warmth from radioactive elements and leftover heat from the planet's formation. Far beneath the surface, pressure would be strong enough to keep water liquid even at temperatures that would normally freeze it solid. These hidden oceans could last for billions of years, offering stable environments that might be considered habitable, despite the darkness and bitter cold above. This idea is not just imagination. In our own solar system, several moons are thought to hide subsurface oceans kept warm by internal energy. Europa and Enceladus are well-known examples, showing that liquid water can exist far from the sun, sealed beneath thick ice, in places that receive almost no external heat. A rogue planet with enough internal warmth could host similar conditions, creating a life-friendly environment completely independent of any star. Finding rogue planets, however, is extremely difficult. They reflect no starlight because they have no star nearby. They glow only faintly in infrared from their own internal heat, and the coldest among them may be beyond the reach of today's instruments. Astronomers have identified some candidates using gravitational microlensing, a method that relies on gravity rather than light. When a massive object drifts in front of a distant star, its gravity can briefly magnify the starlight. By studying these subtle brightenings, researchers have found planetary mass objects that seem to wander freely, though it can be hard to prove they are truly alone and not simply orbiting very far from a faint, unseen star. In one notable study, astronomers reported evidence for several Jupiter-mass rogue planets while surveying the crowded center of our galaxy. Their analysis suggested that such wandering worlds might be as common as stars, though this conclusion is still debated. Since then, additional surveys have uncovered more candidates, and future projects are expected to reveal many more drifting planets. Altogether, the Milky Way could contain billions or even trillions of rogue planets, most of them invisible as they move silently through interstellar space. The coldest of these worlds would likely be very old, small, and poor in heavy elements. A planet formed early in cosmic history, made mostly of hydrogen and helium and later ejected, would contain less radioactive material and would lose heat more efficiently. An Earth-mass planet like this, drifting alone for 10 billion years, might have cooled to just a few degrees above the faint background glow left over from the Big Bang. Its surface could be coated in frozen nitrogen or hydrogen if any atmosphere remained. Temperatures might fall to only a handful of degrees above absolute zero, cold enough that even hydrogen could begin to condense under the right conditions, though the near vacuum of space would complicate this. Such a planet would be wrapped in total darkness, lit only by the distant sparkle of stars and the soft, uniform afterglow of the universe itself. It would wander for billions of years, slowly cooling as it travels, its path shaped by the gravity of passing stars and the gentle rotation of the galaxy. And yet, even in this deep cold, a small amount of warmth could linger inside. The slow decay of radioactive elements would continue, providing a faint but steady trickle of heat in the darkness. If a rogue planet contains a large core rich in heavy elements, the slow decay of uranium and thorium could release enough heat to keep deep underground regions warm for the entire age of the universe. Any life that might exist there would be hidden far below the surface, living in darkness and sustained not by sunlight, but by chemical energy from geological activity, completely cut off from the cosmos above. This idea opens remarkable questions about where life could survive. On Earth, nearly all life ultimately depends on the sun. Even organisms in deep oceans and shadowed caves are part of food webs that trace back to sunlight through photosynthesis. Yet there are also ecosystems that rely purely on chemistry, drawing energy from reactions near hydrothermal vents or within the deep crust. This raises a quiet but profound possibility. Could life begin and continue in a place with no star at all, powered only by the faint warmth slowly leaking from a planet's interior. We do not yet know, but the thought is compelling. If life can endure on rogue planets, then habitable environments might be far more widespread than we once believed. The idea of a habitable zone would no longer be limited to a narrow ring around stars. Instead, it could include lonely planets and moons drifting through interstellar space, as long as they hold enough internal heat to keep water liquid somewhere beneath their surfaces. This would transform how we think about life in the universe and where we might one day search for it. Research into rogue planets is still just beginning. Much of our understanding comes from theory and a small number of observations. Future infrared telescopes designed to find faint, cool objects may reveal many more of these wandering worlds, perhaps even some closer to us than expected. Every new rogue planet we discover teaches us more about how planetary systems form, how worlds interact, and how often planets are thrown into deep space. Each one is also a natural experiment in extreme cooling, showing what happens to planetary material when it is separated from starlight for billions of years. Thinking about rogue planets is also a meditation on cosmic solitude. These worlds travel alone, cut off from the warmth and brightness of stars, wrapped in endless night and deep cold. Their existence stretches our idea of what a planet can be and where it might belong. They remind us that the universe holds far more variety than our Earth-based perspective first suggests. They also hint that cold, rather than being an enemy of complexity or even life, may simply offer a different setting in which matter and energy continue their long story. If we look far enough into the future, the entire universe moves toward an even greater cold. Not just the chill of space as we know it, but a state approaching the lowest temperature physically possible. As the universe expands and energy spreads ever more thinly, everything trends toward a quiet balance known as heat death. This idea from thermodynamics describes a future where usable energy has been exhausted and temperatures everywhere draw close to the same minimal level. It arises from the second law of thermodynamics, which tells us that disorder, or the spreading out of energy, always increases in an isolated system. The universe itself is such a system, with no outside source of fresh energy and no external place to release its waste heat. As time moves forward, energy spreads out. Concentrated forms of energy slowly transform into faint, diffuse heat, and the universe drifts toward a state of maximum entropy, where temperatures even out and no differences remain to power motion, change, or structure. In that distant era, every star will have used up its nuclear fuel. Our sun will end its life in about 5 billion years, expanding into a red giant before releasing its outer layers and settling into a quiet white dwarf. Larger stars live faster and die sooner, some ending in brilliant supernova explosions, others collapsing into neutron stars or black holes. The final generation of stars will fade away roughly 100 trillion years from now, leaving the cosmos without new starlight. After the age of stars, the universe will be filled with their remnants. White dwarfs, neutron stars, black holes, along with scattered planets, asteroids, and thin interstellar gas will remain. These objects will continue to cool, slowly radiating their leftover heat into space. White dwarfs, once bright with stored thermal energy, will cool over immense spans of time until they become black dwarfs, dark, cold spheres no longer glowing in visible light. This cooling takes trillions of years, but eventually even these remnants will approach the temperature of the cosmic background radiation. That background glow itself will not stay the same. As the universe expands, the radiation stretches to longer wavelengths and grows colder. Today it sits at about 2.7 Kelvin. In a few hundred billion years, it will drop below 1 Kelvin, and in a few trillion years it will fall to tiny fractions of a degree above absolute zero. It will never fully reach absolute zero, but it will come ever closer as space continues to expand without end. In that far future, space itself will be unimaginably cold. Any object that does not generate its own heat will cool until it nearly matches the faint background temperature, only fractions of a degree above absolute zero. The remains of planets, frozen solid and long separated from their dead stars, will drift through darkness at temperatures close to the lowest possible in nature. The interstellar medium, already sparse, will thin even further, and whatever warmth once lingered will have long since faded away. Yet on these vast timescales, even matter may not last forever. Some theories in particle physics suggest that protons, the core building blocks of atoms, might eventually decay. Their predicted lifetimes are staggeringly long, far beyond the current age of the universe. If this decay occurs, then after unimaginable stretches of time, all matter made of protons and neutrons would gradually break apart into radiation and lighter particles. Stars, planets, and every familiar solid object would slowly dissolve, leaving behind mostly photons, neutrinos, electrons, and positrons. Even black holes, often thought of as eternal, would not survive forever. Through a subtle quantum effect known as Hawking radiation, black holes emit an extremely faint glow and lose mass over time. For black holes with the mass of a star, this radiation corresponds to temperatures far below today's cosmic background. But as the universe keeps expanding and cooling, black holes will eventually become the warmest objects left. A black hole with the mass of our sun would have a temperature of only a few dozen nanokelvin, just billionths of a degree above absolute zero, softly radiating into the endless dark. A black hole with the mass of the sun is actually far colder than the current cosmic background radiation, so for now it absorbs more energy than it gives off, very slowly gaining mass from the faint glow around it. As the universe continues to expand and the background temperature drops below the black hole's own Hawking temperature, this balance changes. The black hole then begins to lose mass through Hawking radiation, and as it shrinks, its temperature rises. A stellar mass black hole would need about 10 to the 67 years to evaporate completely, while the largest supermassive black holes could last up to 10 to the 100 years or more. Near the very end of this process, the black hole becomes extremely hot and releases its remaining energy in a final burst of radiation as it reaches microscopic size. For almost all of its existence, though, it remains an incredibly cold object, quietly radiating in the darkness of space. Long after black holes have faded, and long after protons may have decayed, the universe would be left mostly with radiation, neutrinos, electrons, positrons, and perhaps particles of dark matter. Temperatures everywhere would be extraordinarily low, shaped only by the continued expansion of space. With no meaningful temperature differences, there would be no flows of energy, no engines for change, no large-scale structures forming or evolving. This state is known as heat death, sometimes called the Big Freeze, the final cold balance of the cosmos. Entropy would be at its maximum, and temperature would hover ever closer to absolute zero. It would never reach that limit exactly, but it would approach it endlessly, passing through millikelvin, microkelvin, nanokelvin, and beyond. In that distant era, the universe would be an immense, dark expanse, disturbed only by the faintest quantum fluctuations in an otherwise still cosmic background. From a human point of view, this future may feel bleak, yet it simply reflects the natural outcome of the physical laws that shape reality. The second law of thermodynamics gently guides everything in this direction. Concentrated energy spreads out, stars exhaust their fuel, matter slowly breaks down, and temperatures move toward a uniform low level. It is not a catastrophe in cosmic terms, only the quiet result of physics unfolding over unimaginable spans of time. Some cosmological ideas offer different endings. If the universe were shaped differently on the largest scales, or if dark energy behaved in another way, expansion might one day reverse. In that case, everything could fall back together in a hot, dense finale sometimes called a big crunch, where temperatures rise instead of fall. Other theories imagine a cyclic universe, with repeated phases of expansion and contraction, or subtle quantum transitions that reset cosmic history in unexpected ways. For now, however, observations indicate that expansion is accelerating and shows no sign of slowing. Dark energy, the unknown influence behind this acceleration, appears steady. If this continues, the path toward heat death remains the most likely future. The universe will keep expanding, thinning, and cooling, moving toward a state of extreme cold over timescales so long that the entire history of stars and galaxies becomes only a brief early chapter in an almost endless cosmic story. Thinking about such distant futures asks us to gently widen our perspective. We are used to seeing the universe as lively and full of motion, with stars shining, planets circling, and galaxies slowly interacting. Yet this busy era is only a brief chapter in cosmic history, a temporary time when concentrated energy is still available to power change and build structure. If our current understanding of physics is correct, most of the universe's future will be quiet, dark, and deeply cold. Even then, true stillness will never fully arrive. Quantum physics tells us that empty space is never completely empty. Tiny fluctuations will continue at the smallest scales, with pairs of virtual particles appearing and vanishing in fleeting moments. In an infinite universe, extremely rare statistical fluctuations might even assemble complex arrangements of matter for short times, a strange idea sometimes described as Boltzmann brains, where order briefly emerges from randomness before dissolving again. These thoughts stretch far beyond anything we can test directly. We are projecting today's physics across immense timescales and energy conditions we cannot yet explore. The lifetime of protons, the nature of dark matter, the long-term behavior of dark energy, all remain uncertain. Our visions of the far future are careful guesses, always open to revision with new discoveries. Even so, the idea of heat death gives us a meaningful way to think about the ultimate direction of the cosmos. Cold is not just a local absence of warmth. It is the long-term trend of the universe itself, the destination toward which all processes slowly move. The second law of thermodynamics is often called the arrow of time, the principle that gives time its direction, and that arrow points steadily toward greater entropy and lower usable energy. Seen in this light, our present universe, warm, structured, and rich with energy differences, is a temporary exception. The early universe began in a state far from thermal balance, with enormous energy packed into a small region. As space expands, that energy spreads out, temperatures fall, and entropy rises. We exist in a middle era, a time when stars still shine and planets still circle them, when enough free energy remains to support the complexity that allows life and awareness to appear. This era, however, is limited, a brief island of warmth in an immense ocean of cosmic cold. There is something humbling in this view, yet also a quiet beauty. The universe spans an astonishing range of temperatures, from the extreme heat in stellar cores to the delicate fractions of a degree above absolute zero reached in our most careful experiments. Across this range, matter behaves in different ways, forming different patterns and revealing different layers of physical law. The coldest realms mark one end of this spectrum, where thermal motion fades and subtle quantum effects become more visible. As you rest and let your breathing grow slow and easy, you might picture yourself drifting through deep space, far from any star, surrounded by the soft glow of the cosmic background. The temperature there is just a few degrees above absolute zero, colder than anything we feel on Earth, yet still warmer than some of the coldest regions known. Around you, thin clouds of molecules float gently, slowly building complexity even in the chill. Far away, a dying star releases its outer layers, creating pockets of cold that approach the lowest temperatures nature allows. On distant worlds, if such places host their own laboratories, curious minds might cool matter to even lower temperatures, exploring strange quantum behaviors and testing the edges of what nature allows. This realm of cold is not separate from the realm of warmth. It is the same universe, the same atoms and energy, simply existing under different conditions. The atoms that form your body were forged in ancient stars, drifted through cold molecular clouds, were heated during the birth of the solar system, cooled again in space, warmed within Earth by radioactive decay, and now rest near 300 Kelvin, balanced by the quiet chemistry of life. These atoms have traveled across the full range of cosmic temperatures, and they will continue to change as the universe evolves. To think about cold is also to think about time. Cold unfolds slowly and with patience. Brown dwarfs take billions of years to cool. The universe itself will need trillions upon trillions of years to approach its final chill. Our human lives occupy only a tiny instant within this immense timeline, a brief pocket of warmth in a far longer, colder future. Yet within this short span, we are able to imagine the whole arc of cosmic history, from a hot beginning to a cold ending, and in doing so we reach beyond our own moment. Extreme cold carries a sense of quiet. At temperatures only billionths of a degree above absolute zero, atoms drift so slowly that their motion feels almost suspended. Time does not truly change, but our perception softens as movement fades and delicate quantum states can linger undisturbed. Within such stillness, we are able to notice effects that would be hidden at higher temperatures, lost in the restless motion of heat. Cold reveals the subtle and the delicate, the quantum patterns that are always present but usually masked by thermal noise. Perhaps this is why imagining cold places can feel calming. When we picture frozen moons, dark interstellar clouds, or stars slowly cooling, we imagine quiet and rest, a pause in constant activity. We imagine a universe where motion slows, where turbulence settles, and where complexity gently gives way to simplicity. There is a kind of peace in this vision, a sense that beneath all the motion and sound of existence lies a fundamental stillness to which everything eventually returns. The coldest regions of the cosmos also teach us about limits. Absolute zero is a boundary that can be approached but never fully reached, a rule woven into physics by quantum mechanics. No matter how advanced our tools become, matter will always retain a trace of motion, a tiny residue of energy that cannot be removed. This is not a shortcoming of our knowledge, but a basic feature of reality. In a similar way, the heat death of the universe marks a limit in time, a final state toward which entropy guides all closed systems. We cannot stop the overall cooling of the cosmos, cannot reverse the growth of disorder, and cannot hold on to the present era of warmth forever. The second law of thermodynamics stands firm in every observation we have made, quietly shaping the past, present, and far future of everything that exists. The universe slowly drifts toward balance, toward stillness, toward cold, and this is not a tragedy, but a natural unfolding written into the laws of physics. It is a direction we cannot change, only understand, and in understanding there can be a quiet sense of peace. Within these vast boundaries, extraordinary things are still possible. The universe we live in now remains warm and structured, and it will stay this way for billions of years. Stars will continue to shine, planets will continue their gentle orbits, and if life exists elsewhere among the galaxies, it has abundant time to grow, adapt, and flourish. The cold future is unimaginably far away, while the warm present is the moment we are invited to experience. Even here on Earth, scientists show us that limits can be approached with patience and curiosity. Each year, matter is cooled to lower temperatures in careful laboratory settings, revealing delicate quantum behaviors that are normally hidden by heat and motion. Records for the coldest temperatures continue to fall, step by step, year after year, bringing us closer to absolute zero without ever quite touching it. In this steady progress, we learn more about the nature of reality itself. Observing the coldest regions of space through telescopes, or studying ultra-cold atoms in quiet laboratories, reflects a deep human desire to understand the universe. We are beings shaped by warmth, living on a world with a gentle average temperature near 300 Kelvin, yet our minds can travel far beyond our natural comfort. We can measure the faint glow of the cosmic microwave background, predict how dim stars slowly cool, and create Bose-Einstein condensates that are colder than interstellar space. This reach of understanding is part of what makes us human, and even this thought can feel calming as you rest and let your mind drift. This ability to move beyond our immediate surroundings through thought, imagination, and careful experiment is one of our most remarkable qualities. The story of cold is woven into the larger story of the universe itself. It begins in the intense heat of the Big Bang, flows through the birth of stars and galaxies, includes the formation of planets and perhaps life, and stretches onward into a distant era of gradual cooling. Cold is not separate from this story. It is the direction in which the cosmos gently evolves, the quiet state toward which matter slowly moves. As you rest here now, there may be comfort in remembering that you are part of this vast unfolding. The atoms within your body carry a history of extremes, traces of the early hot universe, the chill of dark molecular clouds, and the warmth of ancient stars. You exist in a rare and beautiful period, a warm chapter of cosmic history where complexity, structure, life, and awareness are possible. Behind you lies a fiery past that has been cooling for billions of years. Ahead lies a far future that will continue that slow cooling over spans of time almost impossible to imagine. Yet in this present moment, you are here, warm, breathing, aware, able to gently explore ideas about the coldest places in the universe without ever leaving your place of rest. You can picture a distant nebula colder than most of space, an icy moon orbiting far from the sun, or atoms in a laboratory moving with extraordinary slowness. You can understand the science in a simple, relaxed way, appreciate the quiet beauty, and sense the deeper meaning. This soft awareness, this calm connection to the universe, is its own kind of warmth, not a warmth of temperature, but of consciousness, presence, and peaceful understanding, the perfect state for deep rest and sleep. The coldest places in the universe exist far away in space and far away in time, beyond anything we will ever physically reach. We will never walk across the frozen nitrogen plains of Pluto, never drift through the expanding shell of the Boomerang Nebula, and never witness the slow fading of the cosmos in the distant future. Yet through science, observation, and quiet imagination, we are still able to know these places. We can understand them, describe them, and gently place them within our picture of reality. This knowledge does not distance us from the universe, it brings us closer. It expands our awareness beyond everyday life and connects us to the full range of existence, from the blazing hearts of stars to the silent cold of deep space. It reminds us that we are not separate from the cosmos, but shaped from the same matter and guided by the same natural laws. As this journey through the coldest regions of the universe comes to a close, allow a feeling of completion to settle in. You have traveled far in thought and returned safely. The universe holds cold beyond imagination, temperatures that approach the lowest limits physics allows. But it also holds warmth, light, structure, and life. Both warmth and cold are natural parts of one vast, balanced cosmos. Neither is good or bad, neither welcoming nor hostile. They simply exist as different expressions of matter and energy. By exploring these extremes, by contemplating temperatures from near absolute zero to the intense heat of stars, we begin to appreciate the richness and variety of the universe. And in that quiet understanding, there can be a sense of peace. Peace in knowledge, peace in perspective, and peace in recognizing that we are small within the cosmos, yet still meaningful parts of its unfolding story. We can understand the cold even if we could never survive within it. We can create temperatures in laboratories that are colder than parts of outer space. We can think about the far future of the universe even though we will never see it unfold. These abilities are part of what makes human curiosity so remarkable. So now, simply rest in this awareness, in this gentle contemplation of the coldest places in the universe. Let the images drift softly through your mind. Dark molecular clouds, frozen moons, fading nebulae, and clouds of ultra-cold atoms suspended in careful experiments. All of these belong to the same reality, the same universe, the same long story of matter and energy moving through time. The universe is cold in many regions, and over unimaginable ages it will grow colder still. Yet it is also warm where warmth can exist, complex where complexity can form, and alive where conditions allow. We are fortunate to live in such a place and time, where temperature allows liquid water, chemistry, biology, and thought itself. This moment in cosmic history is brief, but that does not make it any less real or precious. As your awareness returns gently to the present, to the warmth of your body and the steady rhythm of your breathing, carry this wider perspective with you. You have traveled in imagination to the coldest corners of the cosmos and returned again. You have reflected on temperatures near absolute zero, on the quiet future of cosmic cooling, and on the delicate quantum nature of matter in extreme cold. This understanding becomes a quiet part of you. It deepens your sense of wonder and reminds you that the universe is far more vast, subtle, and beautiful than everyday life alone can show. The coldest places in the universe remain patient in their stillness, quietly holding their secrets for any mind willing to explore them. They will stay cold long after we are gone, continuing their slow changes and gentle drift through cosmic time. Yet through thought, study, and imagination, we have met them. In doing so, we have touched something deep about the nature of existence itself. So rest in that feeling of quiet understanding, in this soft journey through the idea of cold. The universe is vast and ancient, both warm and cold, simple and complex, mysterious yet slowly becoming known. And you are part of it, always connected to the same matter and the same natural laws that shape stars, planets, and distant clouds of ice and dust. In the calm that follows reflection, there can be peace. In accepting limits, there can be ease. In recognizing our place in the cosmos, there can be meaning. The coldest regions of the universe quietly teach all of this. They reveal the quantum nature beneath reality, the gentle direction of time, and the distant future of matter and energy. Sleep peacefully with the sense that you have explored the far edges of temperature and returned carrying understanding. The deep cold exists far away in space and far ahead in time, waiting at the edges of the cosmos. But here and now, there is warmth enough for life, for thought, and for dreams. And perhaps in dreams, you may drift once more through those silent regions, floating in stillness, watching atoms move more and more slowly as they approach absolute zero, witnessing the quiet beauty of a universe that cools, little by little, toward its final calm state. The coldest places in the universe are not empty or without meaning. They are rich with physics, filled with subtle phenomena, and beautiful in their quiet, minimal way. They are one expression among countless others of what matter and energy can become. By understanding them, we come to understand our universe and ourselves a little more completely. And that understanding, more than warmth or cold, is one of the most meaningful gifts quiet contemplation can offer. So rest now in the gentle comfort of the present, having explored the coldest extremes in thought. The journey settles, but the understanding remains with you. The universe is not built for our comfort, and it does not promise permanence. It follows simple, impersonal laws, unconcerned with hopes or fears. Yet within those laws, during this brief warm era, complexity forms, life appears, and awareness awakens. We are patterns of matter that have learned to look back at the cosmos and understand it. That this is possible at all, even for a short time, is something truly remarkable. When we think about the cold and distant future, we are using one of the most extraordinary abilities we have, the ability to look beyond our immediate moment, to imagine vast stretches of time and space, and to find our place within them. The final cooling of the universe lies so far ahead that it is almost beyond comprehension. Humanity may change beyond recognition or fade away long before then. Yet even now, with brief lives and limited senses, we can understand this future in a quiet, meaningful way. And in that understanding, there is something that feels timeless, a calm awareness that connects the warmth of the present moment with the deep, quiet cold of the far cosmic future. As matter cools closer and closer to absolute zero, the familiar rules that shape everyday life begin to fade, and the strange world of quantum physics quietly comes forward. At ordinary temperatures, the tiny quantum nature of atoms is hidden beneath constant motion. Particles move quickly, collide often, and behave in ways that feel predictable and solid. But when temperature drops to extreme cold, motion slows, thermal energy becomes very small, and the deeper rules of reality begin to show themselves more clearly. In this quiet realm, matter can behave in ways that seem almost dreamlike. One of the most remarkable examples is superfluidity, a state in which certain liquids can flow without any resistance at all. This was first discovered in helium cooled below about 2.2 Kelvin. At this temperature, helium changes into a superfluid, a form of matter unlike any ordinary liquid. A superfluid can slip through extremely tiny openings without losing energy, move along surfaces in thin films, and form delicate whirlpools that follow strict quantum rules. These unusual behaviors are connected to a phenomenon called Bose-Einstein condensation. Helium-4 atoms belong to a category of particles known as bosons, which are able to share the same quantum state. When helium is cooled below 2.2 Kelvin, Many of its atoms settle into the same lowest energy state, moving together as if they were part of a single coordinated wave. In this shared state, part of the liquid becomes a superfluid component that has no viscosity at all, meaning it can flow endlessly without slowing down. Even at absolute zero, helium does not freeze under normal pressure, because quantum motion never fully disappears. Instead, the liquid becomes more and more dominated by this smooth, coordinated quantum behavior, revealing a side of nature that is usually hidden by warmth and motion. The behavior of superfluid helium can feel almost magical when described in simple terms. If you gently stir it and then stop, the motion can continue for an incredibly long time, circling without friction, as if the liquid has forgotten how to slow down. If a container of superfluid helium is placed inside another container, the liquid can slowly climb the walls, spill over the edge, and flow downward into the outer container. This happens because an extremely thin film of superfluid can spread across surfaces and move without resistance, guided only by tiny differences in energy. Rotation in a superfluid is also very different from what we see in normal liquids. Instead of turning smoothly, the motion forms thin, thread-like vortices. Around each of these lines, the fluid circulates in exact, discrete amounts determined by the basic constants of quantum physics. These vortices can arrange themselves into orderly patterns, showing that quantum rules can shape motion on scales large enough to observe directly. Extreme cold also allows another extraordinary state of matter to appear, known as superconductivity. In this state, certain materials can carry electrical current with zero resistance. Normally, moving electrons lose energy as they scatter from vibrations and imperfections inside a material. But at very low temperatures, electrons can pair up and move together in a coordinated quantum state. These pairs flow through the material smoothly, without losing energy as heat. Many superconductors must be cooled to very low temperatures to enter this state, though some special materials can do so at somewhat higher temperatures. Both superfluidity and superconductivity remind us that when heat fades and motion quiets, nature does not become simple or empty. Instead, a deeper layer of order appears, calm and precise, where particles move together in gentle, unified patterns shaped by the subtle laws of the quantum world. In the late 20th century, scientists discovered a surprising class of materials known as high-temperature superconductors. Unlike conventional superconductors, which must be cooled to just a few degrees above absolute zero, these materials can become superconducting at temperatures above 77 Kelvin, the boiling point of liquid nitrogen. Even though this is still extremely cold by everyday standards, it is warm enough to make experiments and applications far more practical. The exact mechanism that allows high-temperature superconductivity is still not fully understood, but the effect clearly shows that quantum behavior can dominate not only in tiny systems, but in large, visible pieces of matter made of trillions upon trillions of atoms. One of the defining features of superconductors is perfect diamagnetism, a phenomenon known as the Meissner effect. When a material enters the superconducting state, it pushes magnetic fields out from its interior. If a small magnet is placed above a superconductor, electrical currents form automatically on the surface of the material. These currents create their own magnetic field that cancels the magnet's field inside the superconductor. The result is magnetic levitation. The magnet can float steadily above the surface, held in place by invisible quantum currents. This levitation is not just a laboratory curiosity. It has practical uses in frictionless bearings, sensitive measurement devices, and experimental transport systems where motion without contact reduces energy loss. As temperatures drop even closer to absolute zero, matter can organize into even stranger quantum phases. Scientists have observed superfluids made from fermionic atoms, unusual electronic states known as quantum Hall systems, materials called topological insulators, and magnetic states referred to as spin liquids. Each of these represents a different way that quantum mechanics shapes matter when heat no longer dominates. The quantum Hall effect, for instance, appears in ultra-thin layers of electrons placed in strong magnetic fields at low temperatures. In this state, electrical conductance takes on precise, discrete values set by fundamental constants of nature, revealing a deep connection between quantum theory and measurable reality. The precision of the quantum Hall effect is astonishing. The measured resistance values are so exact that they serve as international standards for electrical resistance. Different laboratories, using different materials and samples, obtain the same numbers to within tiny fractions of a percent. This remarkable stability arises because the effect is rooted not in the messy details of a specific material, but in fundamental properties of quantum wave functions and topology, a branch of mathematics that describes shapes and continuity. Topological insulators provide another beautiful example of quantum order at low temperatures. These materials behave like electrical insulators in their interior, yet their surfaces conduct electricity through special states that are protected by the topology of the quantum system. These surface states are unusually robust. Imperfections, impurities, or small distortions in the material do not easily disrupt them. Because of this resilience, topological materials are being studied as possible platforms for future quantum technologies, including forms of quantum computing that might resist errors better than current approaches. At extreme cold, quantum tunneling can become more important than ordinary motion. In classical physics, a particle must have enough energy to climb over a barrier. But quantum mechanics allows particles to appear on the other side of a barrier even if they do not have the energy to cross it in the classical sense. This effect enables chemical reactions to occur in environments that seem far too cold for chemistry. In interstellar space, on the surfaces of tiny dust grains drifting through dark clouds, simple atoms can combine into molecules such as hydrogen and water through tunneling processes. Even in near darkness and extreme cold, complexity slowly grows. Cold also changes how we experience the pace of physical processes. As temperature falls, motion slows, and many changes take far longer to unfold. Chemical reactions, diffusion, and relaxation processes all depend on available thermal energy. In laboratory systems cooled to nanokelvin temperatures, such as Bose-Einstein condensates, atoms drift at speeds of only millimeters per second. Quantum states can remain coherent for surprisingly long times, seconds or even minutes, compared to the fleeting trillionths of a second typical at room temperature. In this slowed-down world, delicate quantum patterns can persist long enough to be observed, studied, and gently understood, offering a rare glimpse into the quiet foundations of reality. This slowing of physical processes makes ultra-cold systems perfect for precision measurement. When atoms are cooled and controlled with lasers, they move so slowly and predictably that they can serve as extraordinarily stable references for time. Atomic clocks built from laser-cooled atoms now achieve accuracies better than 1 second over hundreds of millions of years. These are the most precise timekeeping devices ever created. They are so sensitive that they can measure tiny differences in the flow of time caused by gravity, an effect predicted by Einstein's theory of general relativity. Even a height difference of a few centimeters on Earth slightly changes the rate at which time passes, and modern atomic clocks can detect this subtle shift. Extreme cold also creates surprising bridges between different areas of physics. Clouds of ultra-cold atoms can be arranged to mimic the behavior of electrons moving through a crystal, particles interacting inside atomic nuclei, or even quantum fields that existed in the early universe. By shaping laser light into regular patterns called optical lattices and placing atoms inside them, scientists build quantum simulators. These carefully controlled systems allow researchers to explore problems that are too complex for ordinary computers and too extreme to reproduce directly, offering a new way to study the fundamental rules of nature. One of the most visually striking effects at low temperatures is the interference of matter waves. Quantum mechanics tells us that particles have wave-like properties, but this is usually impossible to see in everyday life. In a Bose-Einstein condensate, however, many atoms share the same quantum state and behave like a single, coherent wave. If two condensates are released and allowed to expand until they overlap, they form interference patterns, alternating bands of higher and lower density, much like the bright and dark fringes formed when light waves interfere. The spacing of these fringes depends on the relative motion of the condensates, providing a direct and beautiful demonstration that matter itself has a wave nature. These experiments turn abstract equations into visible structures. In daily experience, quantum mechanics hides beneath the surface. It governs the structure of atoms, the behavior of materials, and the operation of every electronic device. Yet we rarely notice it directly. In ultra-cold systems, though, quantum effects step into the open. The wave function, normally just a mathematical description, becomes something researchers can effectively image and measure. Patterns formed by overlapping matter waves, quantized vortices in superfluids, and collective quantum states in cold gases all make the invisible foundations of reality visible on human scales. As scientists push to lower and lower temperatures, new and unexpected states of matter continue to appear. Each technical advance opens a door to fresh questions. Where exactly does the boundary between quantum and classical behavior lie? How does measurement transform delicate quantum possibilities into definite outcomes? What are the full implications of entanglement, where particles share linked properties across distance? Ultra-cold research does not just confirm existing theories. It also exposes gaps in our understanding and challenges us to refine our picture of the universe. Cold, in this sense, is not emptiness or lifelessness. It is a powerful tool, a way of quieting thermal motion, so that deeper laws can be observed. The record for the lowest temperature ever achieved keeps falling as new cooling techniques are developed. Each step closer to absolute zero reveals phenomena that were previously hidden by heat. The journey is asymptotic. We can come ever nearer, but never truly reach zero. Yet in approaching that limit, we uncover layers of reality that are richer and stranger than anyone once imagined. The search for coldness has driven innovation for more than a century. From early experiments that first liquefied gases, to the creation of Bose-Einstein condensates, to modern space-based laboratories studying cold atoms in microgravity. Each generation builds new tools to explore this extreme frontier. What began as a technical challenge has become a profound scientific journey, one that continues to reshape our understanding of matter, energy, and the quantum foundations of the cosmos. Each advance in cooling technology has opened new realms of physics and enabled new applications. The search for coldness is also a search for understanding, a way to explore the quantum nature of matter by gently removing thermal chaos. The history of cryogenics, the science of very low temperatures, began in earnest in the late 19th century with the race to liquefy gases. Different gases condense into liquids at different temperatures, and reaching these temperatures required remarkable creativity in engineering and experimental design. Oxygen was liquefied in 1877, nitrogen in 1883, and hydrogen in 1898. Each success depended on better insulation, stronger compression methods, and clever ways to let gases expand and cool, and each breakthrough opened new paths for scientific discovery. Helium proved to be the greatest challenge. With a boiling point of only 4.2 Kelvin at normal pressure, helium remained a gas at temperatures where every other known substance had already become liquid. The effort to liquefy helium became one of the major scientific quests of the early 20th century. In 1908, Dutch physicist Heike Kamerlingh-Onnes finally succeeded by using a cascade cooling system, where each stage used a different refrigerant to cool the next stage further. For the first time, temperatures below 5 Kelvin were available in the laboratory, marking the beginning of modern low-temperature physics. Kamerlingh-Onnes quickly began studying how materials behaved under these extreme conditions. In 1911, he made a stunning discovery. The electrical resistance of mercury suddenly dropped to zero when cooled below 4.2 Kelvin. This was the first observation of superconductivity. It showed that entirely new physical behavior could emerge at low temperatures, behavior that could not be predicted simply by extending known laws from warmer conditions. For this discovery, he later received the Nobel Prize. To reach temperatures below the boiling point of helium, new strategies were needed. By pumping on liquid helium and lowering its vapor pressure, scientists could reduce the temperature to about 1 Kelvin. This technique extended the reach of low-temperature research and revealed even more unusual properties of matter in the deep cold. Below 1 Kelvin, researchers turned to helium-3, a rare isotope of helium. Helium-3 has a lower boiling point than the more common helium-4, and refrigeration systems based on helium-3 made it possible to cool materials to fractions of a Kelvin. By mixing helium-3 and helium-4 in devices known as dilution refrigerators, scientists achieved temperatures of just a few millikelvin. At these temperatures, exotic quantum effects in solids and liquids become clearly visible. These refrigeration methods removed heat from a sample through evaporation, close thermal contact with colder materials, or the controlled expansion of gases. For decades, they formed the backbone of ultra-low temperature research, but they also had practical limits. Below about 1 millikelvin, traditional cooling methods become extremely difficult and inefficient. To go further, physicists needed an entirely different approach. That breakthrough came with the development of laser cooling in the late 20th century. By using precisely tuned laser light, scientists learned how to slow down individual atoms. Each time an atom absorbs a photon from a laser beam, it receives a tiny push in the opposite direction of its motion. When the atom later emits a photon, the recoil is in a random direction and on average does not restore the lost speed. Repeating this process many times steadily reduces the motion of the atoms, which means lowering their temperature. Laser cooling relies on the Doppler effect and the quantum interaction between light and matter. Atoms moving toward a laser beam perceive its light as slightly higher in frequency, which can bring it into resonance with an atomic transition. This makes absorption more likely for atoms moving in the wrong direction, gently slowing them down. Using this technique, physicists cooled dilute gases of atoms to microkelvin temperatures, far colder than most conventional refrigerators could achieve. Even laser cooling, however, has a natural boundary known as the Doppler limit, typically a few hundred microkelvin for many atoms. Reaching still lower temperatures required yet more refined methods, continuing the long and creative journey toward the coldest conditions ever produced by human technology. As the temperature drops to extraordinary lows, an interesting limit appears. Below a certain point, atoms begin to gain more heat from the tiny recoil of emitted light than they lose from carefully directed cooling light, and the process naturally slows. To move beyond this boundary, scientists use a method called evaporative cooling. After laser cooling brings atoms to extremely low temperatures, they are held in magnetic or optical traps made of invisible fields. The depth of these traps is then lowered very gradually. The most energetic, warmest atoms escape first, while the colder ones remain behind. Just like the way evaporation cools water on your skin, the average temperature of the remaining atoms continues to fall. With patient control and precise timing, temperatures can reach the nanokelvin range, cold enough for a remarkable state of matter known as a Bose-Einstein condensate to form. The first creation of this state in 1995 required a careful combination of laser cooling, magnetic trapping, and evaporative cooling. This milestone opened the door to an entirely new field of ultra-cold physics and later earned a Nobel Prize. Since then, cooling methods have continued to improve. Atoms have reached even lower temperatures in laboratories on Earth and in the quiet microgravity environment of the International Space Station. Each small step downward in temperature demands greater precision, steadier magnetic and optical fields, longer observation times, and gentler measurement techniques. Yet producing such cold is only part of the challenge. Measuring temperature at these extremes is just as delicate because ordinary thermometers no longer work. Instead, scientists estimate temperature by observing how fast atoms move, reading their motion like a soft whisper of energy. These tiny motions are measured using delicate optical methods such as Doppler spectroscopy and time-of-flight expansion. Even these advanced techniques come with uncertainty, placing fundamental limits on how precisely we can know the temperature we have reached. Keeping things cold is another quiet struggle. Even in the best vacuum chambers, a few stray gas molecules remain, and when they collide with ultra-cold atoms, they bring unwanted heat. Gentle vibrations, faint magnetic fields, and background radiation from the environment all add small amounts of energy. To protect against this, experiments are carefully shielded and isolated, using ultra-high vacuum, magnetic protection, vibration damping, and thoughtful thermal design. The pursuit of extreme cold has inspired new technologies along the way. Superconducting magnets, which help trap and guide atoms, require complex cooling systems and careful engineering. Lasers must be extraordinarily stable and precisely controlled. Every component, from vacuum pumps to electronics, must work reliably near very cold environments. These efforts reach far beyond the laboratory. Atomic clocks built from laser-cooled atoms now measure time with breathtaking accuracy, supporting navigation systems, communication networks, and tests of the laws of physics. Quantum computers that use trapped ions or neutral atoms rely on ultra-cold conditions to preserve fragile quantum states. Ultra-sensitive sensors that measure gravity, motion, and rotation also depend on cold atom techniques, achieving levels of precision far beyond classical devices. In the stillness of these experiments, where motion slows to a near standstill, new windows into the universe quietly open. Ultra-cold physics is now moving into a new and fascinating role as a kind of quantum laboratory for problems that are otherwise impossible to solve. Using ultra-cold atoms as quantum simulators, scientists can recreate the behavior of complex materials inside carefully designed light structures called optical lattices. These lattices act like artificial crystals made from laser light, where atoms take the place of electrons in a solid. By adjusting the light and the arrangement of atoms, researchers can explore how quantum particles interact in situations that would overwhelm even the most powerful classical computers. This approach may help unravel long-standing mysteries, such as high-temperature superconductivity and unusual magnetic states, offering clues about materials that are difficult or even impossible to study directly. The journey toward colder temperatures is also expanding beyond atoms. Molecules, with their richer internal motion, are far more challenging to cool because they can rotate and vibrate in many ways. Still, steady progress is being made. Ultra-cold molecules could open the door to exploring quantum chemistry in slow motion, revealing how particles interact through delicate electric forces and forming entirely new kinds of molecular matter. Researchers are also trying to cool larger objects, including tiny mechanical systems, all the way down to their quantum ground state. These efforts blur the boundary between the quantum and everyday worlds and may lead to new kinds of sensors and tests of quantum theory on bigger scales. Cold environments are also being combined with other advanced systems, placing ultra-cold atoms inside optical cavities, onto miniature atom chips, or alongside superconducting circuits. Each combination creates new ways to control quantum states and new possibilities for quantum communication and simulation. The coldest conditions we know do not occur naturally in space, but are crafted in laboratories, where careful design and deep understanding allow us to create temperatures lower than anywhere else in the universe. It is a quiet triumph of human curiosity and technology, showing that by understanding nature, we can gently push it into entirely new realms. By building these extreme conditions, we uncover deeper truths about the laws that shape reality, about matter and energy, and about the quantum foundation beneath the familiar world. In many ways, the search for cold is a search for simplicity. Cooling matter reduces the restless motion that normally hides delicate quantum effects. As that motion fades, systems settle into their ground state, the lowest energy configuration allowed by quantum mechanics, a state of striking order and clarity. In this calm limit, matter reveals behaviors that are otherwise drowned out by thermal noise, allowing us to study physics in its purest and more fundamental form. We have traveled together through the coldest known regions of the cosmos, from unusual nebulae to distant icy worlds, and into the laboratories where atoms are cooled to temperatures only a breath above absolute zero. We have imagined futures where the universe itself grows ever colder as it drifts toward greater entropy. Along the way, we have found that cold is not simply the absence of heat. It is a condition that reveals new physics, enables new phenomena, and challenges our understanding of what is possible. Cold, in its extreme forms, strips away the complexity of thermal motion and reveals the quantum nature of reality. At everyday temperatures, the quantum behavior of atoms and molecules is masked by their constant, random movement. But as we cool matter toward absolute zero, this motion quiets, and quantum mechanics emerges. Atoms can merge into Bose-Einstein condensates and act as a single quantum wave. Fluids can flow without friction as superfluids. Certain materials can carry electricity with no resistance at all as superconductors. In the stillness of extreme cold, the universe becomes quieter, and in that quiet, its deepest rules are easier to hear. These states are not just strange footnotes in physics textbooks. They are deep glimpses into how matter behaves when energy is steadily taken away, layer by layer, until only the most basic rules remain. The coldest known natural place in the universe, the Boomerang Nebula, forms under rare and fleeting conditions. A dying star sheds material so rapidly that the gas expands and cools faster than surrounding radiation can warm it. At about 1 Kelvin, it shows that nature can briefly approach the temperatures we engineer in advanced laboratories. But this record will not last. As the star continues to evolve, the nebula will warm, and the title of coldest natural place will shift elsewhere, to another temporary arrangement of matter and motion somewhere in the vastness of space. On much larger scales, the cosmic microwave background sets a kind of universal temperature floor. This faint radiation, left over from the early universe, now sits at about 2.7 Kelvin and fills all of space. It is the natural cold that remains when no nearby stars or hot objects are present. Yet even this background temperature slowly changes. In the past, it was warmer. In the distant future, as the universe keeps expanding, it will continue to cool, drifting ever closer to absolute zero over unimaginable spans of time. Closer to home, the icy bodies of the outer solar system show cold shaping entire worlds. On these distant surfaces, gases like nitrogen can freeze solid and methane can exist as liquid or ice. Weather still happens, but at a pace so slow it can take years or centuries to notice change. Beneath frozen crusts, hidden oceans of liquid water may persist, warmed by internal heat. Cold does not mean lifeless or inactive. It simply creates different rules, slower rhythms, and unfamiliar possibilities for chemistry and perhaps even biology. Brown dwarfs and rogue planets add another piece to the story of cosmic cooling. Brown dwarfs, too small to sustain steady hydrogen fusion, gradually radiate away the heat left over from their formation. The coolest among them approach temperatures we might consider almost comfortable by everyday standards, glowing only faintly in infrared light. Rogue planets, untethered from stars, drift toward the cosmic background temperature over billions of years, potentially becoming among the coldest large objects in the universe. These objects blur the boundaries between stars, planets, and other celestial bodies, reminding us that nature does not always fit our classification schemes. Looking far beyond the present era lies the long, slow fade toward heat death. As stars burn out and galaxies grow dark, the universe trends toward a state of maximum entropy, where energy is spread so evenly that no useful work can be done. Temperatures drop, gradients disappear, and physical processes wind down. This distant future, trillions upon trillions of years away, represents the ultimate cold, the endpoint toward which the second law of thermodynamics drives all closed systems. It is a cold so extreme and so pervasive that it encompasses everything, the final equilibrium when all that remains is the faint quantum jitter required by the Heisenberg uncertainty principle. Yet in contemplating this distant cold, we must remember that we live in a warm moment. The current universe, roughly 14 billion years old, retains warmth from the Big Bang. Stars still burn, converting hydrogen to helium, pouring energy into space. Planets orbit in zones where water can be liquid. Life exists, at least here, thrives on these energy differences. This warmth and imbalance will not last forever, but their temporary nature does not make them any less meaningful. They are the reason structure forms, chemistry unfolds, and conscious beings can pause to wonder about the cold depths that surround them. The human effort to produce extreme cold has shown that, with knowledge and creativity, we can build environments colder than any naturally occurring place in the universe. That achievement highlights how deeply we have learned to understand physical laws and how skillfully we can use them. By cooling atoms to nanokelvin and even picokelvin temperatures, scientists have uncovered entirely new states of matter, tested fundamental theories with extraordinary precision, developed transformative technologies, and glimpsed the quantum foundation beneath the everyday world we experience. In these ultra-cold realms, there is a sense of clarity. The ground state, the condition of lowest possible energy, is the simplest arrangement quantum mechanics allows. Matter in this state is stripped of thermal noise and random agitation, revealing its essential quantum character. Reaching towards such conditions is not only a technical milestone, it is also a conceptual one, bringing us closer to understanding what matter truly is when all excess motion is removed. There is also a poetic symmetry between the extremes of heat and cold. The universe began in unimaginable heat, a dense plasma where no stable structures could survive. As expansion cooled that fireball, complexity blossomed. Particles formed nuclei, nuclei formed atoms, atoms formed molecules, and eventually stars, planets, and living systems emerged. Looking far ahead, we see the opposite trend. Continued expansion leads to cooling so deep that structures gradually fade. Stars burn out, matter decays, black holes evaporate. The cosmos moves back toward simplicity, not the fierce simplicity of blazing beginnings, but the quiet simplicity of near-perfect cold and maximum entropy. Between those two extremes, the hot birth and the cold fade, exists a middle era of richness and structure. This is the era we inhabit, a window of time when temperatures allow both stability and change. It is warm enough for stars to shine and chemistry to unfold, yet cool enough for atoms, molecules, planets, and living organisms to persist. This balanced period is limited in duration, framed by the Big Bang behind us and the slow drift toward heat death ahead. Yet within this span, astonishing complexity arises, including minds capable of reflecting on the universe that formed them. The idea of cold shifts depending on perspective. For people, cold often means discomfort or risk, a lack of the warmth our bodies depend on. In physics, cold simply means low temperature and reduced molecular motion. In quantum science, it marks the approach to the ground state where delicate quantum effects become visible. In cosmology, cold represents the long-term direction of cosmic evolution, the gradual cooling that defines the universe's distant future. Each viewpoint captures a different truth, and together they show how a single concept can carry many layers of meaning. As this exploration of extreme cold comes to rest, we can hold a quiet appreciation for cold as a fundamental aspect of reality. It is neither friend nor enemy, only a condition shaped by energy and governed by universal laws. In the coldest realms, the universe reveals subtler patterns, showing us how matter behaves when motion slows and quantum rules step forward. By studying these places, we learn not only about temperature, but about the deep structure of existence itself. Whatever came before the Big Bang, whatever lies beyond our current understanding, you are part of this unfolding, this eternal now, this magnificent and mysterious universe.